My name is Zolta Erdös, and I'm in the next, let's assume 15 minutes. I'm going to try and talk to you about a recent paper that we have published with Susanne Böter and Joya Tetro. It came out this year in Solid Earth in a very similar title. So I'm going to talk about the influence of orogenic inheritance on rift dynamics, and this is, as Kim mentioned, is a numerical modeling perspective. It's going to be a butter and bread style of presentation of just going through kind of the paper and the gist of it. But it's from a project where we were looking at the entire Wilson cycle and trying to understand how orogenic inheritance from the get-go influences rifting. What's the physics behind it, and what are the roles of the different types of inheritance that comes with it. So in the project, we were generally looking at the Wilson cycle from subduction to ocean closing, collision of orogeny, phase of relaxation, rifting, and the opening of an ocean up to a point, basically just to the full continental breakup. But today I will be mainly focusing on this upper right corner of the Wilson cycle, so stable continent rifting and oceanic opening. When Wilson established the framework of this cycle of opening and closure of oceanic basins, he made his point through the example of the North Atlantic, where fragments of both the Pacific and the Atlantic marine faunal realms from the lower Paleozoic can be found on both sides of the Atlantic. So you have Atlantic fauna on the North Atlantic, on the North American side, and then you have Pacific fauna on the European side as well. And he made the point that this only works if there was a collisional origin before, which means that we have now a rifting and opening of an oceanic basin somewhere where we had formerly a suture zone that basically glues together these different faunal realms. And ultimately what this means is that we have the suture. The suture is probably reactivated in some places and possibly not reactivated or not opened up entirely in other places. But it also means in general that we have rifting that doesn't take place in a homogeneous lithosphere to begin with. Which was kind of interesting to bear in mind when we look at rifted margins nowadays, that what we observe, we cannot all trace it back to when we assume a homogeneous lithosphere to begin with. So there are different types of orogenic example. Manachal et al. Classified them in 3 different groups, going from rheological inheritance, structural inheritance, and thermal inheritance. And since they got generally heavily overprinted over time, and especially the thermal one, they can be transient as well. It's kind of challenging to pinpoint examples of these types of inheritance in rifted margins. But I've tried my best, or we tried our best, and looked at the East African rift system, an active rift system, to show examples of how these different types of inheritance might work. So the rheological inheritance might be something that comes from exotic terrains. It might be something that comes from magmatic underplating. Basically, it can be. The root cause can be a compositional difference, compositional anomaly within the lithosphere. So, for example, in East Africa, we have the Tanzania craton that is a strong Archean cratonic block. And as the main Ethiopian rift propagated southwards, it encountered the Tanzania craton, and rather than going through it, it basically split into a western and eastern branch. and go through past orogenic lithospheres that are more easy to deform. For structural inheritance, we can talk about, or we can look at all shear zones themselves, so basically structures that are there. And here an example comes from this Chisi shear zone, I hope I pronounced that properly, from the Ubendium belt. That is a former shear zone, a former suture, Precambrian at age, from that is coming from the collision of the Tanzanian craton and the Banguelo block south of it, and that it hosts now the Rukwa Rift that connects the western branch back to this southern zone of the East African Rift system. And then finally, for thermal inheritance, this is the most challenging one to locate, to give a good example, partly because it's very complex in nature. When you have an orogen, when you have a subduction zone, you might be bringing down cold material at depth, so you might end up initially with a cold lithospheric structure, but you are also bringing in a lot of continental crustal material at some point with this high radioactive heat production. So if you give it time, it will warm up and it will generate a very warm lithosphere. It's also very transient, so time really is essential here. And so the example that I found is kind of an iffy one, but because in Africa, especially, we have the African hotspot that further complicates things. And here up north, in the Gulf of Aden region, we have the Shukra al-Shaikh discontinuity, which is again a shear zone and a weak zone, where there is strong structural inheritance present, and yet there is indication that the presence of the African hotspot, this weaker lithosphere, weakened the lithosphere, and basically by denying the chance for deformation to focus and localize on this pre-existing structure, it stalled the progress of the rift for several million years. So basically here we have thermal inheritance that overprints and overpowers present structural inheritance as well. So just from here, we can see that there are several different ways inheritance acts on rifting. And so the big question that we were trying to answer in these models is, how do these different types of inherited orogenic features influence rifting, and what is their interplay, basically, or what are their relative roles here? So in order to do this, we have been running thermomechanical finite element models. These are two-dimensional models, and they are what are termed accordion models, which means we start out here in this case with an ocean sandwiched in between two continents. We close the oceanic basin. We have a phase of thermal relaxation where nothing happens on the boundaries, and then we open back up the basin. We basically extend the orogen that we have created. In some of our models, there will be, in the models that I'm going to be presenting here, there will also be terrains. These are basically continental or microcontinental terrains that are embedded within the oceanic basin. They're there because oceanic basins tend not to be empty basins, and they provide additional structural complexity and additional inherited structures that we can use in the analysis of these models. I can see I'm at 11 minutes. Thank you, Kim. If you're interested in the technical details, the paper is there. It's out. I'm gonna focus on how these look and show you the models themselves, because I think they're quite informative. So this is a reference experiment. This is the full model domain, so 660 kilometer deep box. This here is 2,000 kilometers wide because there is no microcontinents in it. The microcontinental ones are a little bit wider. The two continents, the oceanic lithosphere and the oceanic basin in between, we have sort of a proto-subduction zone primed in there. I can go back and show you how this looks like. So we have basically some oceanic lithospheric material, oceanic crustal material going down underneath this margin of the model. So if I start this, first I'm in a phase of convergence where I'm closing the accordion. Then I'm stopping motion on the sides of the boundary. So this is the relaxation phase. I have the slab break-off, and then at 130 million year, I start extending, and I extend until I reach full crustal breakup. And the rest of the models that I'm going to show, I'm not going to show the compressional phase because this is a rift seminar and we are interested in the rifting part. And I'm only going to show this box, the inset. The rest of the model is still there, still behind it, but I'm going to zoom in and focus on what happens within the inset. And the rest of the models I'm going to spend more time on, and I'm going to show them multiple times just so you can see better what happens in there. So at the onset of thermal relaxation, this is two models where I had the two microcontinents. So in the shortening phase, they get stacked, and I create these two origins. There's 2 million years of difference between the shortening times of these models. It's the same model. This one I have stopped at 28 million years of compression, and this one I have stopped at 30 million years of compression. The origin size is slightly different. I have in the small colder origin, I have about 4 kilometer high topography and 150 kilometer wide origin, while in the large warm origin, I have more 8-9 kilometers of peak topography and a somewhat wider origin. So this is what I'm starting out with in the relaxation phase. It's the same model up to this point, but I have stopped it at two different times. These plots, these animations, I'm not showing the material properties now, but I'm showing the viscosity field. The darker the colors are, the stronger the material is. The brighter it is, the whiter it is, the lighter, the easier it deforms. Basically, the lower its viscosity is. This is the onset of thermal relaxation. You can see that I have these wide zones in there. They are basically low viscosity areas. I have accumulated a lot of deformation on them. And these models track deformation, and accumulated deformation mechanically weakens the material that's being deformed. This is the large origin, a small origin. They both go to 130 million years in thermal relaxation phase. I'm going to start this one a little bit ahead of the other one because it needed more time steps to achieve that same amount of same time. But you will see that the way the deformation happens, the way the relaxation happens, the way the slab breakup happens is quite different. Here I have this wrenching off of the slab from underneath the origin, while in the other case I have necking at depth and breaking off of the slab at 200-250 kilometers of depth. So immediately I have two quite different types of lithosphere at the onset of rifting then. Looking at in the material domain, we have started out with very similar origins. Here, the blue colors, the blue to black overlay colors, they are accumulated plastic strain. This is basically the zones that have experienced deformation. You can see that for the small origin model, They haven't really been reworked. They haven't really been touched. They are largely undisturbed. And in the large, oh, Jesus, I'm very slow. I'm sorry about that. In the large orogen, I have deformed them quite heavily at depth. In the rifting phase, the small orogen models work like giant core complexes, basically. As I start extending them, mainly the oldest, shortest, steepest suture is the one that is reactivated. That's experiencing most of the deformation, and that's where I have the final rifting happening as well. Whereas in the large warm orogen, the thermal, the extension is more distributed. I have Boudinard style deformation, large scale Boudinard style deformation. I'm reactivating some of the sutures, but I'm also creating a lot of new deformation, including deformation of the original incoming plate as well. So the rifted margins are quite different as well when we look at them. There is a large asymmetry for the small orogen, and really most of the deformation have happened on one suture with some reactivation for the other two as well. But there's not much other deformation within the orogen. While in the large warm orogen, a lot of deformation has happened away from the sutures and within this orogen. So again, looking at it, here I have blue as the cumulative strain, red is what is actively deforming at the time. You can see that mostly I'm reactivating deformation zones that have been active before. So deformation strongly localizes on inherited structures, while in the other model, in the large orogen model, you can see that deformation happens a lot of the places where it has not experienced compressional deformation, it has not experienced shortening, but this is new deformation that is forming these models and deforming these models. What does that mean? If I'm looking at, this is 3 different models, 0 microcontinent, 1 and 2 microcontinents, small orogen, the same 0, 1, 2 large orogen. You can see that the deformation patterns are rather persistent. I have structural inheritance dominating these models with the small cold orogens, and thermal inheritance dominating these large models, overpowering the structural inheritance. And deformation really goes into the previously undeformed lithosphere. So the take-home message really is that rifting of small cold orogens is dominated by the structural inheritance, while large warm orogens is generally dominated by thermal and rheological inheritance. We argue that the balance it's difficult, it's very challenging to decipher which one is more dominant, but we would argue, as you can see on this ternary plot, that the thermal inheritance is probably overpowering rheological inheritance, because the addition of microcontinents, more sutures, and more rheological inheritance doesn't really change the style of deformation that much in these models. Yeah, so thank you for starting the year with us. I'm sorry I really run over time on this one, but if you have questions, I'm still here.
Thank you so much, Zoltan. That was great. It makes it really kind of scary in the sense that it would appear, from what you're showing, that when it comes to interpreting these rift margins after the fact, we almost need to know a hell of a lot more about the pre-rift origins in terms of their style, so that we can identify reactivated structures versus fresh ones.
Yes, I would argue strongly for that it is quite kind of critical to know more about what happened before. What is the thermal, especially what is the thermal state of the lithosphere on the onset of rifting? That can be really paramount. to decipher what structures do we really see, whether they are reactivated, whether they are completely reversed, or whether they are actually new structures themselves.
So you just made everybody's jobs harder.
Sorry about that.